Okay, let's review this problems, these questions in exam number 3. Let's look at the first one. Identify the correct boundary conditions from the following list for the beam shown. Oh, the origin is at A. So this is a key point. Right? The origin is at A. What does that mean? This means your x start from here. Right? This is your x. And at point A, x equals 0. And at point B, x equals L. So we already know that for a cantilever beam, well, the deflection at the fixed end is always 0, and its slope is always 0. So after deformation, this beam cantilever will more or less like this. I will deform in this way. Okay, so our correct answer will be B, right? Deflection equals 0 at the fixed end, and the slope also equals 0 at the fixed end, where x equals L. And for the second one, for the beam shown in this figure, the elastic curve between point B and C for this beam will be a function of x to what power, where our focus will be here from point B to point C. Well, on this section, you can see that the loading added to it is a distributed, constant distributed load, right? So that is to say, our load is a constant. So we showed the procedure of step-by-step integration not long ago, right? So the first one, after one integration, you get the shear. So that will be a function of x. Then bending moment, x squared, and slope, x cubed, and deflection will be a function of x to the 4th. So the correct answer will be A. And number 3, the maximum deflection in the simply supported beam occurs where, okay, we showed this before, right? It's where when you have a zero slope, right? Where you have a zero slope, you will have the maximum deflection. The answer is B. So after deflection in this beam, simply supported beam, when you bend it in this way, the deflection may be like this. Okay, so where you have slope equals 0, you have the maximum deflection. Okay, then number 4. It's a calculation problem. Though the simply supported beam shown consists of a section with I equals a constant that has been given, the E is given, L is given, so M and W have all been given. We just need to do this calculation. But before you do this calculation, as we said, we need to unify those units. In this system, of course, we will do the calculations in terms of this set of units. Newton, mm, and MPa. Since 1 MPa equals 1 Newton per square millimeter. Right, so here our modulus of elasticity, E, will be 200 giga-PA, or 2 by 10 to the 5th Pascal MPa. And the L equals 3 meter, or 3000 mm. And the M is 90 kilonewton meter, or 90 by 10 to to the 6 Newton mm, and the W equals 17 kilonewton per meter, or 17 Newton per millimeter. And we just need to use those numbers to calculate this deflection. Well, this is a superposition method, right? So we just split this beam into two beams. Well, in the first beam, you have a loading like this, by distributed loading. This is beam 1. And in beam 2, you have just one bending moment at this end. So here is your beam 2. Okay, so now we can see that we can select the equations from the big tables for beam 1 and beam 2. Both of them, you just need to calculate the maximum deflection, since this is a calculation of bending moment for the deflection at point B, the largest value on this cantilever. Right? So you just need to select the two equations, then you can calculate the delta 1 from beam 1 will be minus WL, the force, over 8 EI. Right, so delta 2 will be negative ML square over 2 EI. Right, so this total beam deflection at point B will be delta 1 plus delta 2. That will be negative 17 by 3,000 to the 4th over 8 by 2 by 10 to the 5th by 272 million minus 90 by 10 to the 6th by 3,000 square over 2 by 2 by 10 to the 5th by 272 million. So if you calculate it correctly, you will get a negative 3.164 minus 7.445. You will get negative 10.609 mm. So the correct answer is here.